Hello everyone. Um, can I just check that everyone can hear me? Uh, Wait, is it quiet? Okay. Is this better? Hello, hello. Okay. Yeah. Okay. So, hey guys. Welcome to the 2221 or 2121 revision session. Yeah. Then I'll be covering part one from the course. Called linear ODEs. Okay, so let's get started. Yeah, and also if you have questions, just ask on the chat, and I'll try to respond, and then try my best to actually realize that there's questions on the chat. Yeah, okay, so let's get started. Um, Also, there was like the first part of this course, they were like they were like kind of covered in first year. It was kind of like first year revision, so I'll actually skip some of those parts. But those parts, if you still need them, they will be released by MathSoc, I believe, if you want like the entire slideshow for this revision seminar. So, okay, let's get started. Yeah. So, the first definition I want to go through are singular ODEs. There's a simple definition. An ODE is said to be singular with respect to the interval a to b if the leading coefficient vanishes for any x in that interval. For example, this ODE, x u dash minus u equals 0, is singular on 0, 1 because at 0, well, at x equals 0, the coefficient x is 0. It vanishes. So that's what a singular ODE means. Now this definition is going to be important for the next topics I want to cover, so keep that in mind. Yeah, so these are all pretty much the first year stuff. I'll skip over these. Okay, so another definition. These are called initial value problems. And so consider a mth order, so the highest derivative of u is m in the differential equation. So an mth order differential equation, Lu equals f on this interval, a to b. And along with these values, the value of u at a, the value of u dash at a, all the way up to the value of a of the m minus 1th derivative of u. So in total we have m initial values because we get values at the starting point of the interval. So, and this is called, this is called a initial value problem, and it has some nice properties. And here's just a little example. So a third order initial value problem. So the degree of the highest derivative is 3, and we have 3 initial conditions. So that's just a little example. Okay, and this is pretty nice because we have a theorem that says if f is continuous on the interval a to b, and the ODE Lu equals f is non-singular on the interval a to b, then that IVP we just saw, the initial value problem, has a unique solution. And for example, this one is a third order ordinary differential equation, and it's non-singular because the leading coefficient is 1. So it can't be 0 on any interval, pretty much. And if we solve this, we will get a unique solution. Does anyone want me to go through how to solve this? Or can we skip? Because this is also pretty much first year. Yeah, okay, I'll skip this. I'm also happy to skip. And okay, so let's move on. Alright, so there's another theorem, and it's about the homogeneous equations, and I'm assuming you know what that means. So let's say if L is a linear mth order differential operator and non-singular on the interval AB, then the set of all solutions to the homogeneous equation LU equals 0 on this interval, the same interval, forms a vector space of dimension m. Now, what does this actually mean? Well, think vector spaces and bases and linear combinations. This is saying that the set of every single solution to the homogeneous equation LU equals 0, its dimension m. So it has a basis of m, there's a basis for the solution space containing m solutions of LU equals 0. So say that there exists U1 all the way up to UM, which are solutions to LU equals 0, such that every solution to LU equals 0 can be written as a linear combo of U1, U2, U3, blah 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 blah, all the way up to UM. So every single solution is a linear combination of the solutions U1 to UM. That's for homogeneous equations, LU equals 0, and non-singular. Gotta remember that. Okay. So now we can apply a similar idea for inhomogeneous equations, say LU equals F, by fixing a particular solution UP. Then let's say for any solution U to LU equals F, since L is linear, we have L of U minus UP is F minus F, which is 0. What's that saying? That's saying U minus UP is a homogeneous solution. And as we said before, every homogeneous solution is a linear combo of U1 to UM, as we saw before. So pretty much this. The difference U minus UP equals C1 U1 plus all the way up to CM UM. Now if we rearrange, we get U equals UP plus, well, it's just plussing UP on both sides, so we get that the general solution of an inhomogeneous differential equation is UP plus C1 U1 plus blah 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 CM UM. And again, this is kind of from first year, so you should know this. I just went through it just for fun. Okay, moving on. Yeah, these are all just first year stuff. Okay. Alright, so this is some non-first year stuff. Okay, there's this thing called a Wronskian, and the Wronskian is pretty much a tool that allows us to determine whether some functions or solutions of differential equations are linearly dependent or independent. Assuming I'm assuming that you know what those mean. So linearly independent, linear dependence. So the definition is the Wronskian of the functions u1 to um is the m by m determinant wx equals, what's another form of writing it, equals this massive thing. And all this actually means is just for the let's say we had 3 of them, so u1, u2, u3. Let's say these were our functions, m equals 3 pretty much. Then the Wronskian of these functions is just the determinant of those functions on the first row, the derivatives on the second row, and the second derivatives on the third row. That's all it means. And yeah. Now, why is a Wronskian useful? Well, I did tell you you can determine whether some functions are linearly dependent or independent. So here's one lemma. If u1 to um are linearly dependent over an interval, then the Wronskian is 0 for every single value of x in that interval. Now, you can't actually use this to show that some functions are linearly dependent, but we can use the contrapositive to show or determine that some functions are linearly independent. Because the contrapositive is, would anyone like to say what the contrapositive of the statement is? No? Okay, I'll just tell you. Yeah, contrapositive of this statement is just that if the Wronskian of the functions u1 to um. Ah, yes, exactly. Yeah. So if the Wronskian is not 0, then u1 to are linearly independent. And this is more useful because now we can show some functions are linearly independent just by calculating their Wronskian. Now we have another lemma, and it says if u1 to are solutions to this ODE, so am times the mth derivative of u plus all the way up to a0 times u equals 0 on this interval, then the Wronskian satisfies this, I guess, differential equation, involving only just the first leading coefficient and the coefficient after. And to be honest, I haven't seen where this was that useful, so I'm just going to skip over this. It's just a cool fact, I guess. Yeah, okay. Now, okay. We actually have a stronger version of the lemma we saw before, about how if the Wronskian is non-zero, then the functions are linearly independent. But if we add the condition that the functions u1 to are non-singular, and the solutions to the mth linear homogeneous mth order ODE, LU equals 0, then we get some stronger result. If we can only have two things that can happen. Either their Wronskian is 0 and those m solutions are linearly dependent, or their Wronskian is non-zero and the m solutions are linearly independent. This part is pretty much from the contrapositive of the lemma, but this part is the statement that we can't get from that lemma we saw before. And this is pretty useful. Okay, not gonna lie, I don't really like the topics of Wronskians that much, so I'm just gonna skip over quickly. And yeah, so I feel like this one is more useful. And reduction of order is a method of finding a second linearly independent solution to a second order differential equation that's homogeneous, given that we already know one. So okay, if we know a solution u1 that's not trivial to this homogeneous ordinary differential equation, now a second solution is given by this. And so I'll do an example of this. Okay, so question: find the general solution to x squared y double plus 2xy dash minus 2y equals 0, given that y1x equals x is a solution. Okay, so first, we actually have to write the ODE in the form from the previous theorem we saw. In the previous theorem, we require that the leading coefficient is 1. So let's just divide through by x squared for everything. Okay, so we get y double plus 2 on x y dash minus 2 on x squared y equals 0. Now, we know one of them is a solution. y1x equals x is a solution. So let's apply reduction of order. So y2x, a second solution would be, using the formula, the first solution times 1 on the first solution squared times the exponential of the second coefficient, of the integral of the second coefficient. So in this case, 1 on x squared, exponential of integral of this. Wait, no, not that. Jokes, that's not it. This one. Dx. And that is x times 1 on x squared times integral of 2 ln x. So 2 on x is 2 ln x. Oh, do we have to memorize the reduction of order formula? I mean, it's derivable, but I would, because it's just so much faster, and sometimes it's pretty useful. Yeah. It's like, I'm pretty sure it's easily derivable, but yeah, remembering it is, it's just always faster than anything, in my opinion. So yes, I would say yes to that question. Yeah, so continuing on, we get x times 1 on x squared, because the exponential of 2 ln x is the exponential of ln x squared, which is just x squared. And so, running out of space, we get x times the integral of 1 on x4, x to the 4, which is minus 1 on 3x cubed, which is minus 1 on 3x squared. And that's a second solution. Yeah. So these are just written again in the lecture, not the revision session notes, if you want them. Okay. Moving on, we have another method, and this is for only the higher students. So it's called the Annihilator method. And this is a method of finding particular solutions without actually guessing, like we did in first year. Remember, in first year we kind of just looked at the right hand side and we try to guess what the particular solution might be based on that. But this gives us a method of finding a particular solution without actually guessing anything. Okay, let's start with this ODE, LU equals fx. Now, what we do is we try to find a differential operator, A of D, which annihilates f. And that means when you apply it to f, the right hand side, you get 0. For example, D3 annihilates x squared because the third derivative of a second degree polynomial is going to be 0. Now, if we apply this to our differential operator, to both sides of our ODE, we get A of D LU equals 0. And the solution to this homogeneous differential equation will be a particular solution to the original differential equation. Yeah, notice that we went from an inhomogeneous equation to a homogeneous. So a homogeneous solution to this would be a particular solution to this. I think I said that the wrong way around. A particular solution to this would be a homogeneous solution to this. Okay, so let's do an example. Find a particular solution to the ODE y double dash minus 2y dash plus y equals e to the x plus sine x. I should say using the annihilator method. If a question doesn't say that, then you probably don't have to, and it's probably much easier to just try guessing solutions. In this case, yeah, it should be pretty easy to guess. But okay, let's just do this. The left-hand side differential operator is d squared minus 2d plus 1. That just means the second derivative minus the first derivative plus the function itself. And that's actually d minus 1 squared. The function e to the x, which is one of them on the right-hand side, is annihilated by d minus 1. And that's because the derivative of the exponential function is just itself, minus itself is 0. Also, the function sine of x is annihilated by d squared plus 1 because the second derivative of sine is minus sine, and we plus sine to it, we get 0. And so the annihilator, it turns out to be just kind of multiplying these two differential operators. Why might that be? Well, that's because d minus 1, let's say we just apply d minus 1 to this entire right-hand side. Then we get 0 from this, but we get d minus 1 sine x. But if we do this, d squared plus 1 after that, since taking derivatives is commutative, I think, we get that part is 0. So this actually cancels out or annihilates the entire right-hand side. Now we apply the annihilator to both sides. So a of d, which is this, p of d y equals this, because P of d was d minus 1 squared. A of d has a d minus 1. So d minus 1 cubed times d squared plus 1, y equals 0. And the solutions to the characteristic equation for this is 1 with multiplicity 3, I and minus I from this factor. And so the particular solution, we can say it has to be of this form. So essentially, this just gave us a way to, this is like gave us a, the reason why we sometimes guess things like e to the x and multiply by x again, that kind of stuff in first year. This is like a non-guessing method of getting to that. So a particular solution has this form. Now the first two terms in this particular solution are contained in the homogeneous solution of the original differential equation, so we discard them. Notice the first two, e to the x, x e to the x, that's actually part of the homogeneous solution space of this homogeneous equation. Now, why do we discard them though? Why can't we just discard them? Yeah, exactly. If we have, like, there's no point putting those inside the particular solution because it's going to be cancelled out by the homogeneous. Like, if we put this back into the original ODE. And another reason is actually because the general solution is a particular solution plus the homogeneous solution, which is going to be something like ypx plus c1y1 plus c2y2 plus blah 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 cmym. But like if we have some of these in here, it's like we can say like without loss of generality, we can just remove these kind of terms, the terms that overlap in the homogeneous solution space, and that kind of makes our lives easier. We don't need to deal with those little terms over here. And so I'm not going to do this, but if you substitute to the original ODE, just trust me, you're going to get C3 equals half, C4 equals 0, and C5 equals half. So our particular solution is this. Moving on. Another cool technique. Okay, so variation of parameters is a way of getting a particular solution given that you already have two linearly independent homogeneous solutions for the second order ODE case. Now, okay, so let's say we have a linear second order inhomogeneous ODE with leading coefficient 1 in this form. It's a very general form. And let U1 and U2 be a basis for the homogeneous solution space, and let the Wronskian, the Wx, be the Wronskian of those functions U1 and U2. Then a particular solution to the inhomogeneous equation is U equals V1 U1 plus V2 U2, where V1 dash is this, and V2 dash is this. So basically, if we know the general homogeneous solution, then we can find a particular solution. That's all this is kind of saying. And this gives like a really neat formula of finding that. Okay, so let's do an example. Use the variation of parameters method to solve y double minus 3y dash plus 2y equals e to the x sine x. Now the homogeneous solution has characteristic equation t squared minus 3t plus 2 equals 0. So we see that e to the x and e to the 2x, they form a basis for the homogeneous solution space. And the Wronskian, remember the Wronskian was the functions u1 and u2 on the first row, and the derivatives on the second row. The Wronskian is the determinant of that. And so we get 2e to the 3x minus 2e to the 3x, so we just get e to the 3x. So using our formula, our solution is y x equals, just chuck the x away, y equals u1 v1 plus u2 v2, where v1 dash is, remember from here, it's the second homogeneous solution times the right hand side over the Wronskian, and the negative of that, so minus the second homogeneous solution times the right hand side over the Wronskian, and that's just minus sine x. And similarly, using the formula again, v2 dash is this, where this one is the first homogeneous solution, u1, times f, which is the right hand side over the Wronskian again, and we get this for v2 dash. Now it's just a matter of integrating now to find v1 and v2. So integrating these, trust me, this one, the v1 equals cos, and v2 is this. Just trust me, it's just using integration by parts. It's just a bit tedious doing it here. And so the particular solution, we get cos x e to the x minus this times e to the 2x. That's just v2. This is this is v1, this is u1, and this is u2. And simplifying, we get half e to the x times cos x minus sine x. I hope that's simple enough, and I hope you got that. So I'm just going to move on because we're kind of short on time. Okay, so this is like the most time-consuming part of this topic, I believe. So it's the topic of power series. Solving linear differential equations by guessing that the solution has a power series representation. So that's our objective. Find the homogeneous solution by guessing that it is represented by a power series. So consider a very general second order linear homogeneous ODE in this form. A2u double plus a1u dash plus a0u equals 0. Or we can just divide through by a2 to make the leading coefficient 1, where px is just a1 on a2 and q is a0 on a2. Now, let's just assume for now that a0, a1, and a2, they are analytic at 0. That just means they have convergent power series on a neighborhood of 0, some interval containing 0. And let's say also a2, 0 is not 0. Then P and Q are analytic at 0, so we can find power series expansions of both, say these, for some interval containing 0. That's what analytic at 0 means. Now under these conditions, we can guess that a solution is represented by a power series, say uz equals the infinite sum of akzk, az to the k's, and try to find what the ak's are. So this is a theorem. If the coefficients pz and qz from before here, so these ones, if they are analytic on this interval, then the formal power series for the solution uz, this one, it's also analytic for that same interval. This means that if we find where P and Q are both analytic, the power series solutions U is also analytic in that region. So let's do an example. So we aim to construct a series solution to the ODE about the ordinary point x0 equals 0, 1 minus x squared y double minus 2xy y dash plus 20y equals 0, given these initial conditions. And we want to find the solution in this power series form. So the first part of the question, give the recurrence relation for the coefficients an. And this will be illustrated very well if I start doing this example. And I'll get back to these questions after doing that first part. So, okay, we have, let's do it separately. So we want our solution. We want our solution to be in this form. K equals 0, infinity, a k, z to the k. Well, to be a solution, we have to be able to substitute it into the original ordinary differential equation and still get 0. So we should just find the derivatives first. Y dash equals k equals 1 to infinity, a k, z k, and y double is k equals 2 infinity, k minus 1, a k, z to the k minus 2. Forgot a k minus 1 over there. Okay, so let's just substitute this into the original equation. The original equation was this. So 1 minus x squared, y double, minus 2xy dash, plus 20y equals 0. Okay, let's just chuck these in. We already have the derivatives. So 1 minus x squared times that sum minus 2x times the other sum plus 20 times y, which was the sum ak z to the k's, and that has to be 0. Now let's just expand the first sum. So we get k equals 2 to infinity times k minus 1, a k z to the k minus 2, minus the x squared. We can put it into the terms of the sum. So we get k times k minus 1, a k z to the k, minus 2 times, I'll put the x in the term again. So k equals 1 infinity, k times a k times z k, plus 20 times sum from k equals 0, a k z k, that equals to 0. Okay, what can we do now? How can we simplify this? Well, notice that we can actually change these indexes, 2 and 1. We can change those to 0. And that's because changing these to 0 doesn't matter, since the terms we add in are 0. If we add in a k equals 1 term for, say, this one, then we get 1 times 1 minus 1 times whatever, but that's going to be 0. We add a k equals 0 term, we get 0 times whatever, and we get 0. So we can change these indexes to 0. Similarly for this one. And that's nice because we can combine these three sums together. They all sum from the same k values. Let me just add a page. So, where were we? Yeah, so let's combine the sums. The first one stays the same. But the second one, we can combine it to a big sum. I think I'll do a negative instead. So this term, k times k minus 1, a k z k, plus 2 k a k z k, plus minus 20 a k z k. Yep. And that equals 0. We can factorize some things here. We get k equals 2. This is just the first one that didn't change. minus the sum of k equals 0 to infinity of, let's take the akzk out. K times k minus 1 plus 2k minus 20 equals 0. Let's just simplify this. So k minus 1 plus 2k minus 20, that's just k squared plus k minus 20, and that's k plus 5 times k minus 4. So we have the sum minus the sum. Now we can actually simplify this further. If we change this index, shift it by 2, so that k starts from 0, we can add these two sums, like we did before. So we get, by shifting, we get k plus k plus 2 times k plus 1, akz, not ak, ak plus 2 zk minus k equals 0, akzk, k plus 5, k minus 4 equals to 0. Combining these sums, we get, let's factorize out the z to k, get k plus 2 times k plus 1, ak plus 2, minus k plus 5 times k minus 4, ak equals 0. Now, what does this mean for the coefficients? If this whole power series is 0, what does it mean for these coefficients? Yeah, all of them have to be 0. Every single one. Every single one has to disappear. So exactly, every single coefficient, we should say for k equals 0, 1, 2, blah blah blah, we must have k plus 2 times k plus 1, ak plus 2, equals k plus 5, k minus 4, ak. I kind of did two steps in there. I just said this equals 0 and then moved this onto the other side. And we get a recurrence relation by dividing through. So this is the relationship that all of our coefficients have to satisfy. Now, we're not quite done yet here because we need to know what A0 is and A1 is. We need both of them to define this recurrence relation because, as you see, they increase by 2. So it's like we have a relationship for the even terms and we have the relationship for the odd terms. So let's try to find A0 and A1, which are like the starting points of these recurrence relations. How do we do that? Well, we use the initial conditions. If we look back over here, we have y0 equals 1 and y dash 0 equals 0. And that means, so y0 equals, y0 equals 1, y dash 0 equals 0. And since y of x, was it x? No, y of z. Y of z equals the sum from akzk. This is kind of like a Taylor series. The first two terms are kind of the derivatives. So we get a0 equals 1, and a1 on 1 factorial is 1. So a1 equals 1. I'm not sure if this works all the time, but just trust me, a1 equals 0. So yeah, I don't know if this works all the time, but yeah, this is a pretty cool method, I guess. So yeah, a0 equals 1, a1 equals 0. And that is our recurrence relation. So a0 equals 1, a0 equals 0. Now we go back to the second part of this question. Explain from the recurrence relation that one of the series will terminate yielding a polynomial solution. Okay, how do we do that? Well, a1 equals 0. What does that mean for this recurrence relation? It's just, if a1 equals 0, then a3 must be some multiple times a1. But a1's 0, so that's 0. And similar for like every single odd term, they have to be 0. So all the odd terms are 0. And that's kind of not interesting. We don't really care about trivial solutions like that. How about the even terms? Well, a0 or a4, a6, that's equal to 11 times 0 times blah blah blah. Like, it doesn't matter, it's 0 times something, so that's just 0. And similarly to this odd term case, we have a8 equals a10 equals blah blah blah. All of them has to be 0, or a6 as well. So this solution, well, this series terminates. It terminates at a4. And so we get a polynomial solution. We get y of z equals a0 plus a2z squared plus a4z4. Now we just need to find what these coefficients are. And to do that, we just use our recurrence relation we just found. Okay, so a2 is subbing 0 into this recurrence relation. So 5 times minus 4 times, or over, 2 times 1, a0. a0 is 1, so we just get minus 20 on 2, which is minus 10. And a4 would be subbing in 2 to the recurrence relation, and we get 7 times minus 2 over 4 times 3, a1. And that's minus 14 on 12 times minus 10. That's 140 on 12, which is 35 on 3. So our polynomial solution is y of z equals a0, the constant term, so 1, plus a2z squared, which is minus 10z squared, plus 35 on 3z to the 4. And that is our polynomial solution, and that question is done. Okay. So yeah, as I said, these are very, very, very time consuming, and I think the lecturer said something like there's going to be just one of these questions of this kind. So I guess that's very good. So let's move on. We spent so much time on that. Let's move on to singular ODEs. Now remember what I said about singular ODEs? Singular ODEs is just ODEs that the leading coefficient vanishes on the interval that they're defined on. So for example, the Cauchy-Euler ODE, they have this form: ax squared u double plus bx u dash plus cu equals f. Notice the power on the x, power on the coefficient, is like equal to, is equal to the order of the derivative. And so a, b, c here, they are constant with a not equal to 0, for obvious reasons. And this is singular at x equals 0, because x squared is 0 at x equals 0. Now, if we apply this differential operator L to x to the r, we get this. And I'm sure we've seen this before. It's called the indicial equation. This is called the indicial equation, and it looks like x to the r will be a solution to LU equals 0, so like this one is 0, if and only if this indicial equation is 0. So we have these lemmas. Suppose there are distinct solutions R1 and R2 to the indicial equation AR times R minus 1 plus BR plus C equals 0. That is, R1 is not R2. Then the general solution of the homogeneous equation, LE equals 0, that's just going to be a linear combination of those, x to the R1 and x to the R2, for x greater than 0. Now that's simple enough. Now, suppose that there is one solution instead. What if the indicial equation only has one root, say R1? Then the general solution to the homogeneous equation, LE equals 0, is given by this. Select the first one, c1x to the R1 plus c2x to the R1, but times log of x for x greater than 0. Now I want to ask why. Why is this the case? Does anyone know? Yeah, reduction of order. That's exactly right. So reduction of order was how the fact that you can find a second homogeneous solution given that you already have one. And we already have one. This is one of the homogeneous solutions. If we use reduction of order, we're going to get that this is the second homogeneous solution. And yeah, I think you can have a try of that yourself. I won't do it here because we're running out of time, and so I'll just skip ahead. So there's a special case of this. So for a particular solution of the inhomogeneous Cauchy-Euler equation, say just this with like the right hand side being a polynomial, then we can just use the guess that u of x equals alpha x to the r when we're finding the particular solution. And the intuition behind this is just that when we differentiate a polynomial twice, we reduce its degree by 2. But like we kind of make up for it for like each of these coefficients. And this will end up being just like a multiple of just a single power of x. And that allows us to just find what alpha is. Now, even if it's not a polynomial on the right-hand side, for the general case, remember there's always that method of variation of parameters after finding the general homogeneous solution. Remember, variation of parameters was the fact that you can get particular solutions if you have the homogeneous solutions. So just in case you forget this, just use variation of parameters. It will save your life. Okay, so let's just quickly go through this example because there's another example I would like to go through. So find the general solution of this ODE. And so we want to solve the indicial equation first to get the homogeneous solutions. So AR R minus 1 plus BR plus C equals 0. But A equals 2, B equals 7, C equals 3. So this is the indicial equation, and just trust me, the solutions to this are R1 equals minus 1 and R2 equals minus 3 on 2. And so using the lemma we had before, the general solution of the homogeneous equation is this. YH of x equals C1 x to the minus 1 plus C2 x to the minus 3 on 2. Now, as I said, we can find the particular solution by using variation of parameters. And that, trust me, it gives us minus 8x to the 1 quarter. And so we have that the solution is yx equals the general homogeneous solution minus or plus the particular solution we found. But there's a more important example I would like to go through, and it's this one. So I'll add a new page. So find the general solution to the ODE, x squared u double, 2 x squared y plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14 plus 15 plus 16 plus 17 plus 18 plus 19 plus 20 plus 21 plus 22 plus 23 plus 24 plus 25 plus 26 plus 27 plus 28 plus 29 plus 30 plus 31 plus 32 plus 33 plus 34 plus 35 plus 36 plus 37 plus 38 plus 39 plus 40 plus 41 plus 42 plus 43 plus 44 plus 45 plus 46 plus 47 plus 48 plus 49 plus 50 plus 51 plus 52 plus 53 plus 54 plus 55 plus 56 plus 57 plus 58 plus 59 plus 60 plus 61 plus 62 plus 63 plus 64 plus 65 plus 66 plus 67 plus 68 plus 69 plus 70 plus 71 plus 72 plus 73 plus 74 plus 75 plus 76 plus 77 plus 78 plus 79 plus 80 plus 81 plus 82 plus 83 plus 84 plus 85 plus 86 plus 87 plus 88 plus 89 plus 90 plus 91 plus 92 plus 93 plus minus xu dash plus 2u equals 0. So the indicial equation is r times r minus 1 minus r plus 2 equals 0, and that's r squared minus 2r plus 2 equals 0. If we can solve this by just completing the square, and we get r equals 1 plus minus I. So using our lemma, it seems like our general solution would just be u of x equals c1 x to the 1 plus I plus c2 x to the 1 minus I. But we kind of want real solutions. So, and this is like pretty much, it's just not real. Like, it's not always real. So what can we do to make our solution real? Does anyone know? Yeah, kinda, yeah. I think you're trying to say what I'm looking for. Well, we use a little trick. Yes, you can adjust those coefficients to make them real. And the trick is this. We first realized that x to the 1 plus I, well, we can write any number as the exponential of the ln of itself. So exp ln x 1 plus I. And that, just using log laws, we get 1 plus I, exponential of 1 plus I times ln x. And that's exponential of ln x times exponential of I ln x. And that's just x cos ln x minus I plus I sine ln x. Because if you look at this, this is just I think it's called Euler's something. But like, yeah, it's like, this is like the theta in e to the I theta equals cos theta plus I sine theta. But in our case, the theta is ln x, so just put it in. And we get this for x to the 1 plus I. Similarly, we have x to the 1 minus I is x times cos ln x minus I sine ln x. Okay. Now, just add a new page. So we can have a linear combination of these two that is actually real. Two linear combinations, in fact. If we did half of x to the 1 plus I plus x to the 1 minus I, that will actually give us half times 2x cos ln x. And that's cos ln x, or x cos ln x. Similarly, if we do half times x to the 1 plus I minus x to the 1 minus I, actually it should be 1 on 2i, we get 1 on 2i times 2ix sine ln x. And that's x sine ln x. Now we saw that, well, these two are definitely linearly independent. And so, this means that they form a basis for the solution space. We know the solution space had dimension 2 because we knew it was kind of like spanned by these two. And so these two still form a basis for the homogeneous solution space. So the general solution is ux equals different constants, b1 x cos ln x plus b2 x sine b2 x sine ln x. That is the general solution, and that's real. A. Now we're happy. Okay, so moving on. Okay, so there's another form of a singular ODE, and it's called the Frobenius normal form. And it's like more general than the Cauchy-Euler form, and it's z squared u double plus z times some function p of z u dash plus some function q times u equals 0, where p and q have to be analytic at 0. And the way to approach this, we just set P0 and Q0 to be P and Q evaluated at 0, and we define a series F as z to the r times the sum, which looks very familiar from our power series methods, where r is a root of this equation. This is actually the indicial equation of the approximating Cauchy-Euler ODE for this Frobenius ODE. And we have a lemma. So if the solutions to this indicial equation, they're different, then f, the series, replacing r with r1, that is a solution to the Frobenius normal form ODE. And further, if r1 and r2 don't differ by a whole number, then a second linearly independent solution is just chucking in r2 for r in this series. And when it is an integer, it's like super cancel, and I don't think we're going to have to deal with that in the exam. I'm pretty sure our lecturer Chris also said something along those lines. Okay, so this is a Bessel function, or Bessel equation, is a special case of a Frobenius normal form, or the ODE. And it has this form. A Bessel equation with parameter nu is z squared u double plus z u dash plus z squared minus nu squared u equals 0. And this is in Frobenius normal form because the p is 1, that's analytic, and the q is z squared minus nu squared, and that's also analytic. And so it's in Frobenius form with indicial polynomial r times r minus 1 plus p of z at 0, which is r, plus q of z at 0, which is minus nu squared, equals 0. And that's just r squared minus nu squared equals 0, and completing this, not completing the square, using difference of squares, we get this as the indicial polynomial. And also, we seek a series solution in this form. And this is just none other than this we talked about. It's just the z to the r is put into the sum. Now let's just assume that the real part of nu is greater than or equal to 0, so r1 is nu and r2 is minus nu. So like they're the solutions. Now, it's just using, I'll just quickly skim through this because it's just using this power series methods we did even for the non-single case. It's really, really similar. We just have to find the derivatives and chuck them into the original ODE, and that, after a lot of simplifying, we'll get a recurrence relation, just like the one we found in a previous example. And using initial conditions, if we have any, we can find what this we can find what a1 is or a0 is. But yeah, as we keep simplifying down, we see that a solution is given by this equation. So u of z is the infinite sum from k equals 0 to infinity of minus 1 to the k z on 2 times z on 2 to the 2k plus nu over k factorial times gamma of k plus nu plus 1. And that's after setting, or normalizing, we say, the first term to be this. And this is actually called the Bessel function at order nu, denoted j nu of z. And it's going to be a solution to our ODE. Now, if nu is not an integer, then we just get a second linearly independent solution for free, just by chucking in negative nu instead of nu for the Bessel function. And that's a second linearly independent solution. But if it's an integer, then we get some problems. We get, well, we still have one linearly independent solution, but it turns out that the negative n case, if we have the negative n case, then they're actually linearly dependent. Okay, so this question, if we did have r1 equals r2, could we use reduction of order to find another solution? And yes, I suppose. Yeah, that's going to work. But yeah, you can definitely do that. I don't think that's going to be tested in the exam though, because I remember Chris saying it was like super complicated, and just too tedious. But Chris did also mention that for the integer case, when nu is an integer, actually, no, never mind. There's something about Neumann functions when you get into these problems of only having one linearly independent solution. But let's just move on and let's finish off this part of the revision session with this example. So use term-by-term differentiation to prove that for nu and r real number and x greater than 0, the derivative of x to the nu j nu x is x to the nu j nu minus 1x. And hence evaluate that integral. Okay, let's go through this. So x to the nu of the Bessel function of order nu, we can just put the x to the nu inside the fraction, or inside the sum, and put it into the fraction. So the nu, it kind of like goes into here. And the 2 to the 2k plus nu over here. I think there was some steps that were skipped, so I'll just go through them very quickly. This is k equals 0, infinity, minus 1 to the k, x to the 2k plus nu over, we take the 2 out to the bottom of the fraction, we get 2 to the 2k plus nu, k factorial gamma k plus 1 plus nu, all times by x to the nu, and that gives us what we want here, because just add the powers. And to differentiate this, we can differentiate term by term. So let's just take one term of this and differentiate it. Now this looks like super scary and super tedious, but the only thing we're differentiating with respect to is x, and there's only one occurrence of x in here, and it's just simple power rule. So that's fine. That's the derivative of each term. And now we use a property of the gamma function that the gamma of k plus 1 plus nu is k plus nu times gamma of, oh, there's a typo, gamma of k plus nu. And so our derivative, that just becomes this, which is replacing this one, this term, is kind of expanding it out once. But there's a factor of 2k plus nu in both the numerator and denominator. And so we can cancel it out, and we get this term disappears, one of the factors of 2 disappears, and this disappears, and so we get this. So the only things that have changed are the power of 2 moving down by 1, and the gamma going down by 1. Now let's take a factor out of x to the nu, and we just get this. Yeah, so the power decreases by nu on the top. And because the powers now are equal, so the 2 to the 2k plus nu minus 1 and the x to the 2k plus nu minus 1, we can just put the 2 back in on the top. So x on 2 to the power of 2k plus nu minus 1. Now, we just chuck those differentiated terms in the sum. And since the derivative is linear, we can just take out, we can just differentiate term by term just as we did. And so we get this, substituting the derivative we found. And the right-hand side is actually just x to the nu times the Bessel function of order nu minus 1, because j nu of x was minus 1 to the k x to the x onto 2k plus nu, k factorial gamma of k plus nu plus 1. So if we just decrease nu by 1, we will just get 2k x onto to the power 2k plus nu minus 1. Everything else stays the same except for the gamma, which also decreases by 1. And so we're done. That's the first part of the question. Now to find the integral, we just use this fact. So we separate and use integration by parts. So it's just like we're kind of forcing a term to be in this form, because that's like the form we just found, where the derivatives is like, or antiderivative is pretty simple. And so when we integrate by parts, we eventually get this. But our previous result says the derivative of x to the new j nu is just x to the new times j nu minus 1. And so in effect, it's just decreasing the order of the Bessel function. And so the derivative of this, x to the 512 j 512, is x to the 512 j 312. And so this part is just this. So we get, in the end, the answer, the integral is j 312 minus 2j 512 of 1. Okay, that's that question done, and so we're nearly done. And so the final topic I want to cover is Legendre equations. But again, this is just using power series techniques we've seen before. And I'm pretty sure one of the examples we just went through, they were actually a Legendre equation with nu equals 4. And so I won't go through this. It's very simple. Well, not simple. It's just very, very similar to the one we did before. It's just we just assume that the solution is a power series solution, and that's because this is not even a singular equation. And we just eventually find a recurrence relation, as we did before. Yeah, and so, yeah, these are just it's just like another name for these kind of ODEs. So I won't actually explicitly go through these. But yeah, that's part 1 of part 1, first half of part 1 of our revision session. I hope it helped, and I'll hand it over to Joanna, who's doing the second part. Thank you.
Alright, hi everyone, can you guys hear me? Hello. Did I like turn my mic off or something? Nope, looks like the audio capture's working. Or unless I'm not at the bottom. Oh, yes, okay. Okay, so I'm just gonna get started with part 2. So, so part 2 is dynamical systems, and this topic is all about solving systems of first order ODEs. So, just defining some things. There are 2 types of ODEs. One is autonomous and one is non-autonomous. So the difference between them is just that non-autonomous systems depend explicitly on time, whereas autonomous systems don't. So a question that we typically want to answer about ODEs is whether they have a unique solution. And before we really get to that, we're going to define the concept of Lipschitz. So a function defined on a closed interval, a to b, is Lipschitz if for all x and y on this closed interval, the function satisfies this property. So the absolute value of f of x minus f of y is less than or equal to some constant L times the absolute value of x minus y. And the way that I kind of remember this property is that we can kind of rewrite it as this. So the absolute value of the gradient of the secant between x and y is less than or equal to a constant L. So so if the function satisfies this property, it is Lipschitz, and the L value is called a Lipschitz constant. And note that it's a Lipschitz constant because it's not unique. Yeah, so just like covering some theorems with Lipschitz, if a function is Lipschitz, then it is also uniformly continuous. So that means that the property of Lipschitz is stronger than uniform continuity. And a lemma that we have here is that if a function is continuously differentiable over some interval, then it is also Lipschitz over that interval. So continuous differentiability is stronger than the property of Lipschitz. So now let's, go over a question that tests us on our understanding of Lipschitz. So it asks whether this function f, given by f of x equals 2 root x, where x is greater than or equal to 0, asks us where f is Lipschitz. And we can use the property, the lemma that we just looked at, because we know that this is continuously differentiable almost everywhere except the point where x equals 0. And we can see this because when we differentiate, we see that this consists of continuous functions, like 1 on root x, except where x is 0. So it is continuously differentiable. So the function must be Lipschitz on any closed interval where the values in that closed interval are positive. So now we want to test the point where x is equal to 0. So we consider some interval containing 0, and we want to find the gradient of the secant from the point 0 to some other point in that interval. And so, and this helps us because, if we make the other point approach 0, we realize that the gradient of the secant starts to approach infinity. And so we don't have a constant or a finite constant satisfying the property that the absolute value of f of x minus f of y is less than or equal to L times x minus y, where we fix y at 0 and x is some moving point. And so I've kind of just written that out here. So that means that Lipschitz constant doesn't exist for f on some non-empty closed interval containing 0. And so therefore it's not Lipschitz at 0. Or on that interval. Okay, so moving on to the next example. We want to find a Lipschitz constant for the function f defined by f of x equals to x cos x. And one of the theorems that I think are quite commonly used when finding Lipschitz constants is the mean value theorem. So we're going to be applying that here. So to use the mean value theorem, we'll need to the function needs to be continuously differentiable, and we'll also need to differentiate the function. So if we differentiate using the product rule, we get cos x minus x times sine x, and we know that any value is less than or equal to its absolute value. So we just take the absolute value, and then by the triangle inequality, we can separate the two terms out, and we know that it's less than or equal to cos x plus x sine x, taking the absolute value of both of those terms. And we know that cos x is less than or equal to 1, sine x is less than or equal to 1, and so they're absolute values. And so we can say that this term up here is less than or equal to 1 plus absolute value of x, which is less than or equal to 1 plus pi, because x is in 0 is in the interval 0 to pi. So now we can use the mean value theorem. So what the mean value theorem states is that, or in this specific case, is that for any x, we're applying it to any two values in this interval. So yeah, for any x, y, that shouldn't be right. Sorry, that should be like this. So yeah, anyways, a little mistake there. So what was I saying? Yeah, so for any xy in this interval 0 to lambda, there exists and I should state something like x minus y for this interval to make sense. So sorry, that was a mistake. So for any xy in the closed interval 0 to pi, assuming without loss of generality that x is less than y, there exists a c in this interval such that, the mean value theorem would state something like f of y minus f of x over y minus x is equal to f dash of c. But yeah, I'm just like multiplying it on both sides and taking absolute value to get this expression, or this equality. And we know that f dash of c is going to be less than or equal to 1 plus pi. And so therefore, this 1 plus pi is a Lipschitz constant. And yeah, we answered the question. So yes, there was a little mistake here and here because I forgot about how x and y are not necessarily the endpoints. But yeah, we fixed that up halfway. Hopefully no one got confused by that. So we can extend the concept of Lipschitz to vector fields and also vector valued functions. So essentially, we just replace the replace the real valued function with vector valued functions and the real inputs with vector inputs, and we replace the absolute value with the Euclidean norm. I think they're pretty intuitive replacements, so I don't think that should be a big issue, but also it's kind of an issue because we don't really cover this much in the tutorial problems, but that's another story. Anyways, so we also have vector valued functions. We can also define it for like vector valued functions that aren't vector fields. So where there's like the input is like has one more dimension than the output. And it's pretty much the exact same definition, except here we don't have xt minus yt. But this should be pretty intuitive anyway, because the Euclidean norm of xt minus yt is actually the same as this because the t's just get cancelled out. So this definition here should... what this states is that we choose some set S over which we take inputs, and the set S is defined as such. And if f is Lipschitz over this set S and bounded from above, and its Euclidean norm is bounded from above by m, some value m, then this initial value problem, so the generic initial value problem that we've kind of looked at in this course, has a unique solution over this given time interval. And just to be frank, I don't know why this is the case, but yeah. These numbers are like so weird to me. All I do is just remember them, but I don't actually know how they work. But yeah, anyways, we don't really like use this theorem in the problems anyway, so I hope everything's gonna be fine. Anyways, so yeah, and an extra fact, xt is also continuous and differentiable. But yeah, that's pretty much like all we've done with this theorem. We've just like seen it and never really went back to it again, because in the linear case there's a much nicer theorem which doesn't have to deal with those ugly numbers. So let's revise what linear systems of ODEs are. So we have our generic non-autonomous system. And we know that this is linear if we can write f of xt in this form, at times x plus bt, where a is a matrix valued function and b is a vector valued function. And this system is autonomous precisely when a and b are constants. So now we have the nicer theorem, and all we need is that at and bt are continuous, so that means that all of its component functions are continuous over this time interval. And if this property holds, then our generic initial value problem also has a unique solution over that given time interval. So like these two things actually match and don't seem very weird. But yeah, it's nice having a global existence and uniqueness theorem that looks nice. Anyways, but what's even nicer is that we generally only deal with this very special case of linear ODEs, which is when we have a constant matrix and the case where b is equal to the zero vector. And we can write solutions to this general system as this down here. And we're basically just taking linear combinations of the exponential of a eigenvalue times t multiplied by its corresponding eigenvector. So that's one way of finding the general solution to this equation. But another way is to use matrix exponentials. So let's define what a matrix exponential is. So how we define a matrix exponential is that we use the Taylor series expansion, except we replace the real powers with matrix powers. So now that we have the definition, we consider this initial value system, which is quite generic, and we can actually write the solution as the matrix exponential, so e to the power of t a times x0, which is the initial point of the trajectory. So now let's talk about an example that uses the definition of matrix exponentials. So first question, they asked us to state the definition. Well, we just looked at that like 5 seconds ago. Hopefully you didn't forget. So it's just a Taylor series expansion once again. But this is the more interesting question. So show that if V is an eigenvector for eigenvalue lambda of matrix A, then e to the power of A times V is equal to e to the power of lambda times V. And just note that this V is very important because e to the power of A is a matrix and e to the power of lambda is a real value, so we can't just like cross out the V's. So anyways, so let's try solve this problem. So we have e to the power of e to the power of A times V, and we can write e to the power of A as its corresponding Taylor series expansion by definition. And just rearranging, we get this, we want to focus on this term here. So a to the power of k times v. But this is nice because a to the power of k times v is equal to lambda to the power of k times v. And so we can kind of show this by induction, but also just by like intuition. If we just take out a matrix from the a to the power of k pool, then we can rewrite the expression as a to the power of k minus 1 times lambda v, and well, the V remains, and we can just take another matrix out of this like pool of A matrices and get like this. I'm skipping a whole bunch of steps, but you kind of get the point. So we get lambda to the power of k times v. So we can replace the a to the power of k's with lambda to the power of k's, and so what we're left with is the Taylor series expansion of e to the power of lambda, and so we can say that e to the power of a is e to the power of a times v is equal to e to the power of lambda times v. So this result is kind of nice because it kind of shows us that the two different methods that we use to generate solutions to the constant case matrix ODE, they're actually the same thing. So if we just, I guess, expand or like kind of like look back at what we've done so far, we can use the same method to show that e to the power of t times a times v is equal to e to the power of lambda times t times v, where a, lambda, and v satisfy this property. So our eigenvector, eigenvalue thing. Yeah, we can show that this property is also true. And so I'm pretty sure that was like part of the tutorials as well. But yeah, so if we expand this out, so this is our matrix exponential solution. We can replace it, just a rehash on our first method of generating solutions. We had ci e to the power of lambda I t times vi, where vi is the eigenvector corresponding to lambda I. If t is 0, then we just get this thing here. And just putting the e to the power of ta into the summation, this is what we get. And just from our previous result, we can replace this with this. So, and this is the first solution that we got. Yeah, so pretty cool. So now that we've kind of covered the definition of the matrix exponential, we want to find a more practical way of calculating it, because calculating, it will take, in general, an infinite amount of work to calculate infinite matrix powers. So, it would be nice if we could do it nicely. So there are some methods that we covered in class. So the easiest one, I think, is the nilpotent matrix. So if the determinant of a matrix is 0, I'm not sure if it's like guaranteed that it's nilpotent, but I know that if a nilpotent matrix has to have determinant of 0. So yeah, if it's not 0, then we can't really apply this method. But yeah, anyways, so if A is a nilpotent matrix, that is, some power of a to the power of n is equal to 0, then we can sum all the terms in the Taylor series expansion up to the smallest such n to find its exponential. So let's say a to the power of n, so for some matrix a to the power of n is equal to the 0 matrix, then we can say e to the power of a is equal to the sum from I equals 0 to n minus 1 of ak on, gonna change this variable to k, ak on k factorial. So basically we're taking only a finite number of matrix powers, which means a finite amount of work. So that's nice. Another possibility, another method that we've covered is diagonalizing matrices, which we'll talk about in more detail later. And I can't even remember what Jordan form is. Awkward. I don't know. I don't think so. I hope not. I probably need to revise that. Anyways, going back to calculating matrix exponentials. If A can be written as the sum of two matrices that commute, then we can write, so let's say the matrices are B and C, then we can write e to the power of A as e to the power of B times e to the power of C. Yes, Jordan form. Okay, I dropped 2601. Hopefully we don't need to cover that. Okay. Anyway, so then this isn't really like a method that we use to actually like find the matrix, the exponential of the matrix, because we'll need to actually find e to the power of B and e to the power of C, and we can look to these methods to do that. So yeah, anyways, moving on. So now we're going to kind of revise diagonalizing matrices. So just to define what a diagonalizable matrix is, so some matrix A is diagonalizable if there exists a matrix M such that the inverse of M times A times M is a diagonal matrix. So the definition itself is kind of vague. It doesn't really give us a practical way of finding such a matrix M, but luckily we've done that quite a bit already, and we just choose the matrix M as the matrix of eigenvectors of the matrix A, and the diagonal matrix that results from this is a diagonal matrix of eigenvalues. So and also the eigenvalues correspond to the eigenvector, like the columns correspond. Yeah, so that's kind of like a quick revision of how we diagonalize matrices. But how does this help us? So we have this helps us calculate a to the power of k, because a to the power of k, some diagonal matrix, can then be written as M, which is the matrix of eigenvectors, times lambda to the power of k, which is the matrix of eigenvalues, times the inverse of the matrix of eigenvectors. And this is good because lambda is a diagonal matrix, and powers of diagonal matrices are really easy to calculate. And so, as shown here. So now we get on to like how this helps us calculate exponentials of diagonalizable matrices. So if A is a diagonalizable matrix that can be written as M times lambda times inverse of M, then e to the power of A is equal to M times e to the power of lambda times the inverse of M. And the exponential of diagonal matrices are also very easy to calculate because we just exponentiate the eigenvalues along the diagonal. Similarly, e to the power of t times A is equal to M times e to the power of t times lambda times times the inverse of M. And e to the power of t times lambda, similarly, we just exponentiate the terms along the diagonal and leave the rest at 0. So that was calculating matrix exponentials. We'll kind of move on to the next subtopic now, which is equilibrium points. So first, just revising what an equilibrium point is. So A in Rn is an equilibrium point if dx on dt equals f of x, if like a satisfies this property, f of a equals 0, which means that if the trajectory starts at the equilibrium point, then it never moves from the equilibrium point. Anyways, so so that means that a solution to an initial value problem where the initial point of the trajectory starts at the equilibrium point is just this constant function. Yeah, anyways, I don't know if I said that very coherently. But yeah, so an equilibrium point is just like where if a solution starts there, it stays there because f of a, which is dx on dt, is 0. That was probably a lot more concise. So a question that we often want to ask about equilibrium points is whether or not they're stable. And there are two types of stability: neutral, neutral stability and asymptotic stability. So we'll first talk about neutral stability. So an equilibrium point is stable if for every epsilon greater than 0, there exists a delta greater than 0, such that if the initial point is within delta of the equilibrium point, then the trajectory here, xt, stays within epsilon of the equilibrium point. So that means that if a solution starts close enough to the stable equilibrium point, then it has to remain close to the stable equilibrium point. So now we define asymptotic stability, and this is a stronger form of stability. So as opposed to like neutral stability, we define asymptotic stability on some open subset. And we say that an equilibrium point A is asymptotically stable on that open subset if A is stable and whenever the starting point is within that open subset, then the trajectory heads towards the equilibrium point as t goes to infinity. And we call this open subset N the domain of attraction for A. So intuitively, this means that not only do solutions stay close to the equilibrium point, but they also approach the equilibrium point as time goes to infinity. So yeah, I feel like with the asymptotic stability definition, we kind of forget about the open subset thing because we have much nicer properties when, once again, we have an autonomous system that is linear. So let's talk about that. So in the linear constant case, just as a reminder, it's ax plus b, where a and b are now constants. The equilibrium point of this system is given by minus the inverse of a times b, and the solution to this system is given by this expression here. And you don't really have to remember this. We can kind of derive it by using our integrating factor method with matrices. So we have, let's say we have an equation of this form. Ax t plus b. Then we can move stuff over. And then multiply by the integrating factor, which would be e to the power of minus a. E to the power of minus a times xt equals e to the power of minus a b. And we know that these two matrices commute just as a property. And so we can write this as d on dt times e to the power of minus a x t, and that's equal to e to the power of minus a times b. And then we can just like integrate using our initial conditions, and our final result should be this. So in this linear constant case, which is what we want to get to, we have much nicer properties for stability. So suppose we have that system dx on dt equals to ax plus b. This system, the equilibrium point minus inverse of a times b, is stable if and only if all real components of the eigenvalues of a are less than or equal to 0, and asymptotically stable if and only if the real components of the eigenvalues are strictly less than 0. And in the second case, and this is the nice thing about this linear constant case, the domain of attraction is the whole of Rn. So I think that's like why we kind of forget about the fact that asymptotic stability is like defined on an open set, because in the cases that we deal with, we don't have to worry about that. So now we'll go on to trying to sketch phase portraits for 2D linear systems. And this table kind of provides a summary of what we're going to look at in more detail, like now. So in the case where we have two positive real eigenvalues, so I have an example here. Like, let's suppose we have this system. So dx on dt is equal to ax. And let's suppose that we found the eigenvalues. It's 1 and 2, and their corresponding eigenvectors are 1, 2, and 1, 0, respectively. I'm just going to, from now on, call lambda 1 the smaller eigenvalue. Lambda 2 will be the larger eigenvalue, and v1 will be the eigenvector corresponding to the smaller eigenvalue, and v2 will be the eigenvector corresponding to the larger eigenvalue, because they're kind of a mouthful to say if I don't replace it with these shorthand versions. So we found the eigenvalues and eigenvectors. So we know that the solution has this form shown here. So how do we draw the phase portraits? So step 1, we should draw the eigenvectors draw the lines corresponding to the eigenvectors. So that will be these two red lines that you see in this diagram. And to draw some other trajectory other than the eigenvectors, like the lines corresponding to the eigenvectors themselves, we start our trajectory somewhere close to the origin, and initially the trajectory should stay close to v1, and then as time goes on, the trajectory goes in the direction of v2. And like how I remember this is that I like to think of like t as being negative, like at the starting point, and then t becomes more and more positive as time goes on. So when t is like negative, this term will dominate, and so the trajectory sticks close to that eigenvector, the line corresponding to that eigenvector. And then as t goes to infinity, this the second term starts dominating, and we so our trajectory starts going in that direction. So that's how we draw phase portraits in the case where eigenvalues are real and positive and also distinct. I almost forgot about that point. And obviously, since the eigenvalues are positive, the node is unstable. The equilibrium point is unstable. In the case where both eigenvalues are negative, suppose we have that same system, dx on dt is equal to ax. We want to determine the stability, or we want to like kind of draw the the trajectories around that equilibrium point. We know that this equilibrium point is stable because both eigenvalues are negative. But yeah, so we know that, like, we know once we draw the trajectories, we know like how to draw the arrows on them. But how do we actually draw the trajectories? So once again, I'm going to refer to lambda 1 as the smaller one, lambda 2 as the larger eigenvalue, v1 as the eigenvector corresponding to the smaller eigenvalue, and v2 as the eigenvector corresponding to the larger eigenvalue. So the difference between the current case and the case that we're looking at right now is that in this case, we should start our trajectories further from the origin. So I kind of like to think of the start of the trajectory as like where t is negative. And so when t is negative, this term starts to dominate, or is dominating. And so our trajectory should be in the direction of 1, 1, which is this line. Well, not 1, 1, but like rather minus 1, minus 1. But yeah, it's parallel to 1, 1. And then we draw our trajectory so that it's heading towards the origin. But as it does that, t gets larger, and so the second term starts dominating, and so our trajectory starts going in the direction of 2, 1, which is v2. So we kind of replicate that with every other trajectory that we draw, like so. And yeah, so that's the case where both eigenvalues are negative. So in the case, oh yeah, and I forgot to add the extra detail that they should be negative and distinct. In the case where the eigenvalues are equal, we have two types of nodes. So one is where, one is where the eigenspace is one-dimensional. So the line corresponding to the eigenvector is just one line for both of the eigenvalues. The other case is where all non-zero vectors are eigenvectors. So in this case, every trajectory is either a straight line away from or towards the origin. So those are the two cases that can happen when the eigenvalues are equal. Now is the case that we've kind of covered pretty extensively in class. So this is the saddle point where the eigenvalues are opposite in sign. So the way we draw these trajectories is we start off by drawing the lines corresponding to the eigenvectors as always. So in this case, lambda 1 is minus 1, v1 is 2, 1, lambda 2 is 1, and v2 is 1, 0. So we start off by drawing the lines corresponding to the eigenvectors, and we start with the way we draw the trajectories is that we start off with our pen close to v1, which is the eigenvector corresponding to the smaller eigenvalue. So that will be, say like for this trajectory, that will be up here. And then, okay, I think I screwed up this one. It should be 1, 2. Sorry about that. Just because the y is like the larger term. Yeah, I wrote that here, but not here for some weird reason. Anyways, I'll fix that before we post the slides. Anyways, so we start our pen close to v1, or like the line corresponding to v1, and our trajectory heads slowly towards the origin, but as time goes on, the v2 starts dominating, and so our trajectory starts heading in that direction of v2. or the line corresponding to V2. And as for the trajectories along the lines themselves, for the negative eigenvalue, the trajectory should go towards the origin, and for the positive eigenvalue, the trajectory should go away from the origin. So just like drawing the arrows on this example, the trajectory should look something like this. So now we've kind of covered all of the cases where the eigenvalues are real. We're now going to cover the case where eigenvalues are non-real. How did you make it so there are equations? Text on the left and an image to the right. I don't know if this is a good way of doing it, but I just use mini pages. Yeah, just look up LaTeX mini pages and you'll see some magic. Anyway, so in the case where the eigenvalues are non-real, we have a specific case where the real components are 0, and so the eigenvalues are purely imaginary. So if the eigenvalues are purely imaginary, then the trajectory forms orbits around the equilibrium point. And we can determine whether this orbit is clockwise or anti-clockwise by finding the value of dx on dt at a point. So in this case, let's say we substitute in this point, which might be 0, 1. We want to find dx on dt, and that's ax. So at this specific point, dx on dt is equal to a times 1, 0. That's going to be equal to some vector. And according to this diagram, you'll probably find that the vector points in this direction. So you'll know that the orbit goes in an anti-clockwise direction. I hope my clockwise and anti-clockwise directions are correct. But yeah, so in this case, the orbit is anti-clockwise. So that's a case where lambda 1 and lambda 2, so the eigenvalues, are purely imaginary. In the case where we have a non-zero real component, we have a spiral. And the spiral can either go inward, so an asymptotically stable equilibrium point, when the real component is less than 0, or the spiral can go outwards when the real component is greater than 0. And we can determine whether the spiral is anti-clockwise or clockwise by, once again, substituting in a point and finding the value of dx on dt. So in this case, let's suppose we substitute this point in, and that is probably 0, 1. So we'll find what 0, 1 is. That's going to be equal to some vector. And according to this diagram, that vector should point in this direction. So we know that the spiral is in the anti-clockwise direction. Because you know how spirals can go like this, or they can go like this. So substituting in a point will help us find which way the spiral rotates in. Anyways, so now we'll be doing a problem on equilibrium points. So this question asks us to solve for xt and yt and determine the type and stability of the equilibrium point of this system of differential equations. So you can rewrite this in the dx on dt equals to ax form. And so that gives us this equation down here, and where a is equal to 1, 1, 2, 0. And so now we want to solve for this system. So so let A equal to that matrix that we saw just now. And by solving this equation, so the determinant of A minus lambda I, which is the identity matrix, is equal 0. If we solve this, then that helps us find the eigenvalues of A. And the eigenvalues of A are -1 and 2. And the eigenvectors are 1, -2, and 1, 1. Oh, they are like one of the eigenvectors for like each of the eigenvalues. And just as like a refresher, we just solve A minus lambda I equals 0 for each of the eigenvalues, and that's how we find the eigenvectors. Wait, should be like this, sorry. Equals 0. Yeah, so we solve this for V, and that's how we find the eigenvectors. So now that we have that down, we can write our solutions in the form xt equals to the sum from I equals 1 to n of ci e to the power of lambda I t times vi, where vi is the eigenvector corresponding to eigenvalue lambda I. And yeah, so when we write it in this form, we can equate the components xt and yt, and we get that xt is equal to c1 times e to the power of minus t plus c2 times e to the power of 2t, and yt is equal to minus 2 c1 times e to the power of minus t plus c2 times e to the power of 2t. Yeah, so that's just by equating the components. So we've answered the first half of the question, and we should always remember to check to make sure we've answered the full question. And the second part of the question asks us to find the equilibrium point, determine the type and stability of the equilibrium point. So we didn't actually need to find the equilibrium point, but yeah, it's at 0, 0, because we know that in this form, B is equal to the 0 vector, and so the equilibrium point, which is minus the inverse of A times B, is equal to 0. So like, yeah, the equilibrium point is 0, 0. Yeah, but we know that one eigenvalue is positive, and so the equilibrium point must be unstable. And we can classify this as an unstable saddle point because the eigenvalues have opposite signs. So yeah, so it's an unstable saddle point. And now we've answered the question, I hope. Anyways. Okay. Yeah, so now we go on to the topic of first integrals. So first we define what a first integral is. So a function g is a first integral for a system of ODEs, our very generic system, or generic autonomous system, if g applied to any solution trajectory is a constant. So we can kind of write that, or we can write it as g of x is equal to a constant c. And so if we differentiate this with respect to t, then we should get the gradient of g of x dotted with x prime, I'm getting all my words mixed up, dotted with x prime of t equals 0, because if we differentiate a constant, we get 0. So we know that x prime, or x dash, oh my god, I'm turning American, x prime is equal to f of x. So we can write this as the gradient of g of x dotted with f of x equals 0. And so that means that the gradient of G and F are orthogonal, and so that's how we get this property here. Exactly, I watched too many of his lectures. Now I say prime instead of dash. Anyways, so now let's solve this problem relating to first integrals. And this is our last problem, so that's nice. So we have this system of ODEs, and we want to prove that G is a first integral, where G of x is given by x1 squared plus x2 squared. So we can write this system as d on dt, x1, x2 equals x1, x2 minus x1 squared. So we can make this equal to f of x, and so that's how we get the right hand side of the system, having this equation thing here. So remember, we want to take advantage of the fact that if G were to be a first integral of this system, then we must have the gradient of G dotted with f is equal 0. So to do that, we need to find the gradient of G. And just as a reminder, the gradient of G is given by partial G on partial x1, partial G on partial x2. So since G is equal to x1 squared plus x2 squared, then the gradient must be 2x1, 2x2. So now we take the dot product with the gradient of G and F, and we find that, yes, the dot product is 0, and so G of x must be a constant for all solutions of dx on dt equals f of x. And geometrically, this is nice because it tells us that any solution to this system of ODEs must lie on some circle, because x1 squared plus x2 squared has to be a constant, and so the trajectory must lie on a circle. And I guess the benefits of first integrals we've seen are that they give us geometric properties of the solutions, and they also sometimes help us find a solution to the system. So that's the end of part 2, or part 1. Part 2 of part 1. Hopefully you guys didn't fall asleep, and thanks for watching.